Alright, so our video is on fairness criteria. In the previous lesson, like prior to this, we talked about the different voting systems. That's what we see up here in this chart. And to start off, we're going to explain the Pareto principle fairness criteria, which is if a voter prefers, like if everyone prefers alternate A over alternative B, then B can't win. So I drew a little chart down here as an example of that concept. You'll see right here that alternative A, for example, is a cat, alternative B is a dog. In each of these, the voter prefers the cat over the dog, so the dog can't win. And looking at this chart, you'll see that the Pareto principle works in all of the different voting systems except for our voting with a fixed agenda. And our next one is Condorcet criteria, which is when you match up all the alternatives against each other and one wins every single time it's matched up. So this only works when you have the fixed agenda voting system.
So the next one is monotonicity, which means that if alternative A is the winning alternative in a voting system, but then A is moved up in someone's preference list, then A should always still be the winning alternative. So if you switched A and B here, then obviously A should still win. So for the independence of irrelevant alternatives criteria, it basically means that, say, if you choose apple pie over cherry pie, and then you're also asked to rank apple, cherry, and pumpkin pie, no matter where pumpkin pie falls on that ranking, it shouldn't affect whether you like apple pie better than cherry or not. Apple pie will still be better than cherry, no matter if pumpkin pie is up here, or here, or here. And then if it does change that, then it violates the criteria.
Okay, here we're doing problem 10.2 in the book, and it's going to be problem 3, and we're going to see if the border count satisfies the Condorcet winner. So here we have 3 freshmen trying to get on the student council, and they took a vote of 103 students, and 32 of those students put Susan, Courtney, Jade, 55 put Courtney, Susan, Jade, and 16 put Susan, Jade, Courtney. And if you got in 3rd place, you would get 0 points. If you got in 2nd place, you would get 1 point. And if you got in 1st place, you would get 2 points. So, doing the border count method, if we go over the first box, Susan would receive 64 points. Courtney would receive 32 points. And Jade would receive 16 points. Then let's just say we add up all of Susan's points. Here we got 64, 55, plus 32 would equal 151. We add up Courtney's points would be 32, 110, and 0, which would be 142. And Jade would get 0, 0, and 16. So the border count winner would be Susan because she had the most points. And let's go to the pairized method of comparison. We already have it written down, but we did Susan v. Courtney, and Susan won the block 1 and block 2, and she would receive 48 points. But Courtney won block 2, which is a power of 55 points, so Courtney would beat Susan. And then you got Susan versus Jade. Susan beat Jade in every single category, so she got a total of 103 points. So Susan would be the winner versus Jade. Then you got Jade versus Courtney. Jade only beat Courtney 1 time, so she got 16 points. Courtney beat Jade twice in the 32 and the 55 box, so she got a total of 87 points. So the pairized winner would be Courtney, and the border count winner would be Susan. And how do we find the Condorcet winner? Would be matchup between every single person, and whoever wins against every single person is the Condorcet winner. So here the Condorcet winner theoretically would be Courtney, but the border count winner was Susan. So the border count winner fails the Condorcet criteria. And then we have it right here in our chart.
So our next problem is problem 7 from 10.2, which is asking us to find the winning destination for a class trip. And we have New Orleans, Chicago, Atlanta, Charleston, and Jacksonville as our choices. It's asking us to find the winning destination using the plurality with elimination method. The work is shown right here. New Orleans wins that. Then it asks us to take out Chicago from all these spots. If we do that, we see that the results don't change and the outcome stays the same. So the final part of this problem is asking if it satisfies the irrelevant alternatives criterion, which it does. But over here on our chart, we say it does not satisfy the criterion. So one difficult thing about this whole fairness criteria is that sometimes you'll encounter situations where it'll sometimes work, as you can see in this problem. Because eliminating Chicago has no effect on the outcome.
One thing that you have to remember about the fairness criteria is that if it does not satisfy, if a fairness criteria doesn't satisfy a voting method, that doesn't automatically mean that every single time it's not going to satisfy it in every situation. It just means that there's not a guarantee that it will satisfy it. But if there's a check mark, if it does satisfy the criteria, it will every single time, no matter what.